Well, how exciting! You have made it to the last section for the entire semester. You are almost finished with business calculus. That's an awesome accomplishment because this class is by no means easy. So good job on your perseverance. In section 15.4, we're looking at the fundamental theorem of calculus. That's a pretty important theorem. So take some time to read the text, go through your first page of notes, and when you've completed that, I'll work through some examples with you starting on example 2. I'll work examples 2, 3, 4, 5, and 6 in this video. When you're ready to begin example 2, notice that we're calculating a definite integral. So I have limits on my integral sign. A lower limit of integration, that's the 2, and the upper limit of integration, that's the 5. So we're going to execute this in a couple of steps. The first thing I want to do is find the antiderivative, just like I normally do in an indefinite integral. So I'm going to integrate term by term, starting with 6x squared. When we integrate, we get constant 6 times x cubed over 3. Then we work to our next term. We have constant 3. Applying the power rule to x, we end up with x squared over 2 is the antiderivative. And for our constant 5, that one gains an x. Now normally if we're working on an indefinite integral, we have a plus c out there, but that's not necessary for a definite integral. So I'm going to go ahead and close brackets, and now we need to evaluate this from x equals 2 to x equals 5. So we're going to plug in, actually first let's simplify, and then we'll start plugging in our limits of integration. So I notice right here I can reduce that just a little bit. And maybe I'll write that second term a little neater so that it's easier to read. So we have 2x cubed. Let's rewrite that second term as 3 halves x squared and then plus 5x. So what we're going to do next is plug in our upper limit of integration, which is 5. Everywhere I see an x. So we have 2 times 5 cubed minus 3 halves times 5 squared plus 5 times 5. Once I evaluate the upper limit of integration, then I'm going to plug in my lower limit of integration, which is 2, everywhere I see an x. Now you got to be careful here because I'm going to be subtracting more than one term, so I need either parentheses or brackets here so I correctly distribute that negative. Now we're plugging 2 in for x. So we have 2 times 2 cubed minus 3 halves times 2 squared plus 5 times 2. Okay, so this is all arithmetic. You can take as many steps or as few steps to calculate this as you want. You can plug it into your calculator and put it in all in one step if you want to. I'm going to take just a couple of steps to evaluate it. So 5 cubed is 125, and 125 times 2 is 250. Next, I have 5 squared, which is 25, times 3 halves. That gives me 75 over 2, and plus 25. Then I'm going to subtract my lower limit of integration. So I'm going to keep my parentheses here for a minute. 2 cubed is 8, and 8 times 2 is 16. Next term we have 2 squared, which is 4. Notice we're dividing by 2, so that gives me 2 times 3, which is 6, and then plus 10. Okay? Now, again, at any point you can choose to enter this into your calculator. I'm going to evaluate what's in that red set of parentheses and then plug it into my calculator. So get some workspace here. We have 250 minus 75 over 2 plus 25. Now inside parentheses we have 16 minus 6, which is 10, and then 10 plus 10 is 20, so we have minus 20. Okay? So pulling out my calculator here, I have 250 minus 75 divided by 2. Let's see what came next. Plus 25 minus 20. So we have plus 25 minus 20. And I'm expecting the result to be a fraction, so I'm going to go ahead and have my calculator turn it into a fraction. You just press your math button and choose number 1 fraction. And we end up with 435 over 2. So the final result, 435 over 2. and that is a definite integral, applying the fundamental theorem of calculus. So really, up to this step, you're integrating like you normally would, and then you have a few calculations to finish out your definite integral. So let's try our next example. On example 3, we're finding the integral from 1 to 2 of dy over y. Now, don't let that notation confuse you. This is the same thing as the integral from 1 to 2 of 1 over y dy. Now, hopefully you recognize the antiderivative of 1 over y is natural log of the absolute value of y. That part is the same, just finding the antiderivative. And then I'm going to run this from 1 to 2. So applying our fundamental theorem of calculus, we plug in our upper limit of integration. Notice 2 is positive, so absolute value bars are really unnecessary. I can just write it natural log of 2 minus natural log of 1. Now, do you remember what natural log of 1 is? That's equal to 0. Of course, if you forgot that, you could type it into your calculator and find that information very quickly. So the exact value for our definite integral there is natural log of 2. Sometimes when you're evaluating definite integrals, you're still going to need that substitution process. So in this section, you're going to be reviewing all of your rules of integration and then tacking on that fundamental theorem of calculus at the end of your problem. So let's consider the integral from 0 to 5 of x times the square root of 25 minus x squared dx. In order to find the antiderivative, we're going to have to make a substitution. We can let u be our radicand 25 minus x squared. We know that as soon as we choose our u substitution, we immediately differentiate both sides of that u substitution. So du on the left, and the derivative of 25 minus x squared is negative 2x dx. So when we get ready to rewrite our integral, we know that the radical part is going to be rewritten as square root of u. And then remember, we've got some leftovers. We have x dx left over. We want to isolate this x dx so that we can see what our leftovers will be replaced by. So multiply both sides of that substitution equation by negative 1/2. And we can see that our x dx will eventually be replaced by negative 1/2 du. Okay, so if you drop down here and check out this line, notice I have the square root of u as my new integrand. There's my negative 1/2 du. So that part is just like the substitution rules that you've been practicing. What's different about it is we're calculating a definite integral this time. So that means I have limits of integration. So when I change variables from x to u, it's going to affect those limits of integration. Keep in mind, this is the relationship between x and u. We know that in the original integral, because my variable of integration is x, that both of those limits of integration are x values. I want to change them from x values to u values using this relationship. Okay? So let's consider our lower limit of integration, which is 0. When x equals 0, and I plug it in here, u is 25 minus 0. I'm looking at this second line here. Okay? So when x is equal to 0, u is 25 minus 0 squared, which is going to give me 25. Okay? Considering our upper limit of integration, which is 5, and plugging it into our substitution equation, you can see that right here. When x is equal to 5, then u is 25 minus 5 squared, which comes out nicely to 0. Okay? So when I replace my lower limit of integration, x equals 0, it's going to become u equals 25. So in this position, I want to put the corresponding u value, which is 25. My upper limit of integration was x equals 5. The corresponding u value there was 0. So when I replace my upper limit, I'm going to put the corresponding u value, which was 0. Okay, so that's the only new part when we're doing a definite integral by substitution. Rewrite everything in terms of u like you normally do, but don't forget to update those limits of integration. You can't plug in x values if you're working with the variable u. Okay, now we're ready to integrate like normal. We have coefficient negative 1/2, And let's think of this square root of u as u to the 1/2. That way, whenever I integrate it, I'm going to add 1 to the exponent. 1/2 plus 2 over 2 is 3/2. And we divide by that same value. Now, we don't need the plus c because we're not doing an indefinite integral. We're working a definite integral. Let's clean it up just a little bit. Let's rewrite it. Negative 1/2 times 2/3. Remember, when we're dividing by a fraction, it's the same thing as multiplying by the reciprocal. Times u to the 3/2 from 25 to 0. Okay, let's simplify our coefficients a bit. I need one more line in here for an extra step. We have negative 1/3 u to the 3/2 from 0 to 25. Nope, pay attention here. How about 25 on the bottom, 0 on the top? Okay, so next we're going to apply our fundamental theorem of calculus and plug in our upper limit, 0. So we have negative 1/3 times 0 to the 3/2. And we're going to subtract our antiderivative evaluated at the lower limit. I'm going to be careful and put a set of parentheses right here. So plugging in our lower limit, we have negative 1/3 times 25 to the 3/2. So our first term goes away. That's a 0. Notice here we have a double negative. We could make that a positive. And let's work on 25 to the 3/2. Okay, 25 to the 3/2 is the same thing as the square root of 25 to the 3rd power. Remember that denominator becomes the index of your radical, and if it's a 2, we normally don't write it. So that's 5 to the 3rd power, or 125. Okay, so I have 1/3 times 125. Don't forget, your calculator is useful if you panic and you can't remember how to do it. Type 25 in your caret key, type in your exponent 3/2 and evaluate. You'll come up with 125. So my final answer here, I'll go back to the answer blank, is 125 over 3. So that's the exact value for our definite integral. So remember, if you have to make a u substitution, make all of your changes. That is, replace your integrand with its expression in terms of u, replace dx with some multiple of du if necessary, and change your limits of integration. Go from x values to u values using your relationship between x and u. Okay? Now, definite integrals have some pretty cool applications. Area happens to be one of them. So when you're calculating the area between a curve and the x-axis, you use a definite integral. For example, find the area of the region between the x-axis and the graph of x squared minus 3x from x equals 1 to x equals 3. Now, if you need to take some time and go through the text and try and understand what all that means, feel free to do that. When you get ready to work this example, you can restart the video and work it with me. First thing that I want to do is get a visual of this problem. So we need to graph the function f of x equals x squared minus 3x. That's simply a parabola. It opens up. You could find that out very quickly with your graphing calculator if you're not familiar with the function. Let's think about x-intercepts. If I set this equal to 0 and I factor out an x, do you notice that my two x-intercepts would be x equals 0 and x equals 3? So we'll plot our x-intercepts at x equals 0 and x equals 3. And we know this parabola opens up because my leading coefficient is positive. So we're going to get something about like this. Okay? That's sufficient to sort of visualize what's going on. We want to find the area of the region between the x-axis and the parabola from x equals 1 to x equals 3. So x equals 1 is right here, and x equals 3 is this intercept. So I want the area between the curve and the x-axis from x equals 1 to x equals 3. So I want to calculate the area of that shaded region. Well, that's not a normal, ordinary geometric space, so we don't have a formula to apply to it, but we can calculate the area using a definite integral. Now, from your reading, you probably discovered that using a definite integral to calculate area can sometimes produce a positive area, sometimes produce a negative area. So if I consider the area between this curve and the x-axis, and I calculate this with the definite integral, this would come out to be positive area, and this would come out to be negative area. But when I'm calculating the total area, I'm going to ignore the sign on the bottom there. So in our particular example, example number 5, notice the area of the region in question is below the x-axis. So when I calculate this with a definite integral, the answer is going to come out negative. Well, I'm just going to change that negative sign using absolute values. Okay? So the area of the region between the curve and the x-axis, shaded there in green, is given by the integral from 1 to 3. Notice these are my x values, left to right. This is my function in question. That's our parabola. We're going to integrate that from 1 to 3. Again, the reason for the absolute value bars in this problem is because since the region is below the x-axis, we would get a negative number for our answer. Okay, let's work on calculating the absolute value of this definite integral. No substitution is necessary on this problem. So we can go ahead and integrate term by term. The antiderivative of x squared is x cubed over 3. And the antiderivative of 3x is 3x squared over 2. And we need to run this from 1 to 3 using our fundamental theorem of calculus. So plugging in our upper limit for x, we have 3 cubed over 3 minus 3 times 3 squared over 2. There's our upper limit. We're going to subtract the antiderivative evaluated at the lower limit, which is 1. And then we'll find the absolute value of that. Okay, so let's work on our calculations. 3 cubed is 27. 27 divided by 3 is 9. Looks like we have another 27 right here. 27 over 2. Working on our second parenthetical element, we have 1/3 minus 3/2. Okay, so I'm going to type in that middle part into my calculator, starting with 9 minus 27 over 2. Then we're going to subtract, in parentheses, 1/3 minus 3/2. So in parentheses, losing my calculator here, minus, parentheses, 1/3 minus 3/2. Let's turn that into a fraction to see our answer. And we come up with, notice, negative 10 over 3. So the solution inside these absolute value bars is negative 10 over 3. So notice, since the value of the definite integral is negative, that simply indicates that the area we're calculating is below the x-axis. But if we want to just measure the area and not indicate its direction, we just ignore the sign. So the area of that region is 10/3 of a square unit. Okay, so required area is 10/3 of a square unit. So we just calculated the area of an irregular region using a definite integral. So you can see that the application of the definite integral to calculate strange areas, things that are not rectangles or triangles or perfect circles, is really, really a useful skill. Okay, let's try one more example with area. Example number 6. Find the area between the x-axis and the graph of f of x equals x squared minus 4 from x equals 0 to x equals 4. Sketch the graph in the space below. So again, notice we're working with a parabola. Y equals x squared minus 4 is a parabola that opens up. If I want to make a quick and easy graph, I could sketch the x-intercepts. Notice we set y equal to 0, we factored it. The two roots of that equation are negative 2 and positive 2. So I have a parabola that opens up with x-intercepts at negative 2 and positive 2. But notice we want the area of the region from x equals 0 to x equals 4. So I'm going to draw it out a little further. So x-intercept -2, x-intercept 2. That helps me to imagine my parabola. We'll do something like this. May not be drawn to scale, but we've got a basic visual. So the problem says find the area between the x-axis and the graph from x equals 0 to x equals 4. Well, x equals 0 is right here. So I want the area between the curve and the x-axis. Notice I get this region right here, but if I go all the way to x equals 4, then I have some of my area above the x-axis, some of my area below the x-axis. So remember, area below turns out to give us a negative value for our integral. Area above the x-axis gives us positive area. So what we're going to have to do to calculate the total area is to break it up into two integrals. In each case, I'm going to be integrating my function, x squared minus 4. So notice my integrand in each case is that parabola, but I'm breaking it up into two problems. Looking at our first area, the area below the x-axis, x goes from 0 to 2. So my limits of integration are from x equals 0 to x equals 2. Now, do you understand the purpose of these absolute value bars? Again, that's going to ensure that the answer turns out positive. That'll allow us to calculate the total area of the region. Without those absolute value bars, this would come out to be a negative number, and it's going to cancel out some of the positive area that I get from that second integral. So again, the absolute value bars help us to calculate total area. So this is region 1. This one calculates the area of region 1. Okay, let's look at region 2. In this case, the area is above the x-axis, and x goes from 2 to 4. So I'm still integrating my parabola, this time from x equals 2 to x equals 4. We know that this integral should come out positive, so no need for absolute value bars. Okay, now let's execute the work. Working on my first antiderivative, I'm looking at integrating x squared minus 4, term by term. The antiderivative of x squared is x cubed over 3, and the antiderivative of negative 4 is negative 4x. We're going to run this one from 0 to 2 and take its absolute value. Okay? Now the good news is for that second integral, the antiderivative is the same. So we have x cubed over 3 minus 4x, but we're going to run this one from 2 to 4. So working on that first one, plugging in our upper limit of integration, which is 2, we'd have 2 cubed, let's go ahead and calculate as we go, over 3, minus 4 times 2, which is 8. When we plug our lower limit of integration in for x, notice both of those terms zero out. So that's pretty convenient. Working on applying the fundamental theorem to our second antiderivative, we're going to plug the upper limit 4 in for x. 4 cubed is 64 over 3, and 4 times 4 is 16. There's our upper limit. Let's plug in our lower limit, x equals 2. We'd end up with 8 thirds minus 4 times 2, or 8. Okay? So let's simplify this a little bit. Let's start with 8 thirds minus 8. Now, after all that integration, your brain does get tired, and you have a tendency to make arithmetic mistakes. So let me encourage you to use your calculator to be accurate. Okay, so negative 16 thirds is the value of 8 thirds minus 8. So I have right here absolute value of negative 16 thirds. Okay, which is of course going to be positive 16 thirds. Now I'm going to type all the rest of this into my calculator at once. 64 over 3 minus 16. Then I got to be careful here. When I subtract my lower limit, I've got to put that in parentheses. So I'm going to do minus parentheses 8 thirds minus 8. Parentheses 8 thirds minus 8. I want the answer to appear as a fraction, not a decimal, so we end up with 32 over 3. So we have negative 16 over 3 plus 32 over 3. When we take the absolute value there, that's positive 16 thirds plus 32 thirds, which gives us 48 over 3. And that reduces nicely to 16 square units. Okay? So if we want to analyze this, make sure we understand what we did. This region 1 has a total area of 16 over 3 square units. The area of region 2 has an area of 32 over 3. Now remember, on region 1, we had to change the sign to make it positive. So the total area is the sum of the areas of those two regions, and that's how we came up with 16 square units. Okay? I'm going to leave it up to you to finish out example number 7. That's your last example in your notes for the semester. So when you complete that problem, have yourself a little celebration. Congratulations on completing all of the notes. I know you've worked very, very hard, so thank you for your perseverance and hard work. All you have to go is finishing out the homework, your last chapter exam on MyMathLab, and finally our final exam. If you have any questions or concerns, as always, please send me an email. Y'all have a great day.